Okay, so again, what they observed for what Thomson and Stoletov observed was that for positive voltages, okay, uh, the the photocurrent that they measured through their circuit was independent of the voltage, but was proportional to the light intensity that they shined on one of their electrodes. But what was interesting is that the negative, if they applied negative voltages, okay, then they saw the current decrease linearly, and furthermore, they saw that it decreased, that for any intensity, okay, the current decrease, the photocurrent would essentially turn off below a particular negative voltage, V naught, negative V naught, which I've indicated here. So basically, no matter how much intensity they shined on the this one electrode here, they could turn off the photocurrent at a particular voltage, again, which is independent of the intensity. Okay. Now, a couple things. First of all, they did not observe as they kept in the regime where they had a positive voltage here. Okay, then they did not observe a threshold intensity for which they got no photocurrent. So that is, they can keep reducing the intensity, and they'd keep getting lines like this. Okay, and it would just keep getting closer and closer to no photocurrent, but they didn't see a threshold photocurrent, that is one below which they couldn't they got no photocurrent at all. Okay, and so this basically is the first indication that their assumption that a light is a wave is incorrect, at least with respect to these measurements, because if light were a wave again, and the intensity and the energy, the amount of energy in the wave depended on the intensity of the light, then there should be some threshold um, intensity value below which you couldn't liberate any electrons, because again they're attached somehow to the atoms of the material, and it takes some minimum energy to basically liberate them, okay, so to ionize them. And they didn't observe that. And then of course, again, the interesting thing that there was a unique value for a particular metal. There was a unique value of the what they call the stopping voltage, okay, which is or the stopping potential, okay, which below which they don't get any photocurrent, okay, and which is independent of the intensity of the light. Okay, so I've written that discussion here in words. When the voltage applied is positive, that is when you put a positive charge on this plate, then the current is proportional to the light intensity, and there's no threshold intensity, okay, below which we get no photocurrent. When the voltage is less than zero, that is when you reverse the polarity. That means you put a negative charge, okay, on this plate relative to this plate, okay. Then the current decreases in proportion to the voltage, okay. And finally, when the voltage is below some threshold minus V naught, there's no current independent of the intensity, okay. So if we apply a negative, in the regime where we apply a negative voltage to this plate, that is when we're in this part of the graph, that means that we're putting negative charges on this plate. And if the light is basically kicking out electrons, kicking out negative charges, it would make sense that we should be able to bring that we should be able to repel those electrons from this plate, and therefore get no photocurrent. Remember, in order to get a current, you have to get charges to flow around the whole circuit, which means that somehow charges have to get from this plate to the other plate, even though there's vacuum inside. And that means, again, that if you liberate electrons, they have to go from here to here. So if you apply a negative voltage, which is big enough over here, then you should be able to repel those electrons depending on their initial kinetic energy when they leave the plate on the left.